Thanks to everyone. I want to give a particular shout out before I get started to my wife, who is probably streaming this at home. We are such great partners, and we rely on each other. And when I said, "Hey, I think I'm going to put in to give a talk, and I'm going to disappear for a few days right at the last week of school," and she said, "Great, go, do it." And if my kids are live streaming this, put down your phone, you're in school. You could watch it later. All right. I was going to title this talk something involving Altium and the horses they rode in on. I decided that not to do that, in part because I like horses and they don't deserve to have their reputation tarnished by being associated with Altium. After a brief intro to me and to NCX, I'll talk about how we came to pick Altium, because it's important to know why that even happened to start with, because I was the decider. I picked. And I thoroughly regret that decision. And then I'll talk about why we moved to KiCad. And then I'll change the tone dramatically. And I'm going to talk a little bit about how we deal with library management. Because while you can just run the install and you can get the standard libraries, it's not quite clear exactly how you go about dealing with libraries that are yours internally that you can't reveal maybe for privacy reasons or security reasons. And you don't want to be leaking what you're building indirectly by releasing your components into a public library. You may be able to do that after you've done loads of projects, and you might do a big dump of everything so no one could quite tell exactly what's going on. And then I'm also going to talk about output generation and how we're using the JobSets now. This is a critical feature for me, and it works mostly. I'm glad to have in the audience the people who can do some things about that. Some of these things are small, and they'll go away. My goal is one-click output generation. Tons of files, one click, consistent, and ready for manufacture. Why should you listen to me, right? This is the first thing. I'm about to tell you that you should dump a very expensive tool that perhaps your company is very committed to, that you have a lot of intellectual property intertwined with it. So I thought I'd let you know a little bit about myself and where I came from, my origin story. My father was the senior registrar for the graduate school for the City University of New York. And as you can imagine, as computing is just starting to happen, keeping track of classrooms, students, grades, courses, transcripts, this is like a really straightforward and obvious use of computing. And so even though he has a degree, or had, may he rest in peace, he had a degree in geography. He was a very early user of computing. And so, even as a kid, I would have to go to school with him. School would be closed. There would be no one to watch me. I'd go into work with him, and he would go on his teletype, and he'd print out giant, Snoopy was one of them, and I would color for hours on his floor under his desk. And we had in our elementary school, we had a single Apple IIe that for an hour a week I got to program with a partner. We couldn't save anything, so you had to retype your program in every time. And I programmed in Logo, and we made drawings. And my father saw how excited I was about this, and he managed to find a class at Manhattan College for kids. And so I started to learn BASIC on a Commodore PET. And along the way, I'm playing next door with my buddy, and his father comes home. His father owned 3 pharmacies, and they sold Timex watches. And one quarter, he had a great quarter and sold a mess of watches, and Timex sent him a Sinclair. And so he comes home, and he tosses this Sinclair. He's exhausted, and he throws this thing at us, tosses it on the bed, and he says, "I don't know what to do with this. Here, you have it." And both of us have been in computing ever since. I have told him how grateful. He doesn't even remember doing it. He was so tired. uh, and so these were things that really helped. Now, in the mid-'80s, growing up in Yonkers, New York, the city, thanks to redlining and city policies on public housing, they utterly segregated the entire city. And Judge Sands put an end to that in 1985, which was right before I entered high school. And so they wanted to try and avoid the violence that occurred up in Boston when the schools were integrated. And so to get people to go to different schools willingly and to get on a school bus and cross the city, they created programs, magnet programs they called them. I see this term around now. It's not always used the same way. But they literally wanted to attract a student to get on a bus and go into a neighborhood, some of them not such great shape, let's just say, and be willing to do that. And so I don't know how this happened, but I am so grateful to Miss O'Rourke, Mr. Tooley, and Mr. Healy, because when I graduated high school from the computer science magnet program in 1989, I could program in Pascal, Fortran, COBOL, and I did a little bit of assembly language. And there was no IT staff, so we had rooms of IBM PCs, and we all learned how to fix them, which kept me employed when I got to college. This was just fantastic. When everybody else was making minimum wage, I was making like triple. So I founded 4 businesses. The first one of them was just a sole proprietorship. I'd been making telecommunications supercomputers that were all used to birth audio and video and data conferencing. Nothing has changed. 35 years, every call still starts off with, "I can't hear you, can you hear me?" Nothing has changed. And so we built DSP farms. And we had some really talented contractors at the company that I landed in that had designed the first one. I learned from them. And my degree is in physics. I took 2 electronics classes and then realized that I like to touch things. And that's why I didn't go into computer science when I got to Carnegie Mellon to start with. Something just didn't feel quite right, even though I was pretty talented at programming. And so after I spent a little stint there, I decided to leave there and form my own little contracting business. My goal was to start up. So I was mostly working with a bunch of people that I knew, and we were all trying to do it better than Cisco. Some were more successful than others. And eventually, I formed a company called Maygold, where we were going to basically utilize motorized blinds in tall buildings to run ads down the front of them, so that you can close without bothering people. You turn all the lights on in the building, and you open and close the blinds, and you can make dot matrixy kind of images down the front. And we were just getting that business off the ground when I had a tremendous opportunity, and I ended up taking it to go out to Seattle and work on one of Bill G's pet projects. And so I took all that knowledge of the DSP farms, and I architected the machine vision system for the hardware for the machine vision system for the first Surface table. And I didn't like working at Microsoft so much, so I split off. Eventually, they became a very good customer of mine. And that was where I formed Goldstein, and play on my name, for those of you who know the periodic table. And I've done just a number of projects for them. First for the Applied Sciences Group, which is not Microsoft Research. They're their own beast. And there I built force-sensitive touch sensors. I built 256 LEDs in a strip that run along a perfectly designed and highly calculated piece of plastic in the background. And with it, you could steer the beam of light coming through an LCD display. So you run the display at 240 or 480 hertz, and you could alternate the images you're showing, and you can basically project out to your 2 different eyes or to 4 different people. I mean, imagine playing a card game where everyone's playing and seeing their own full HD screen. It is a cool technology. It's super expensive. It's never going to be sold. And so I eventually I moved on, and I did some work for Oculus. I did work with Magic Leap. I eventually landed a gig with the hardware lab at Microsoft Research. You got like well over 1,000 computer scientists. Most of them don't know how to make hardware, but they have great ideas for hardware. And so rather than have to go and negotiate individual contracts with each company for each project and then deal with change orders and all of that sort of stuff, they have one group that's like it's a contract engineering firm with no contracts. And they operate on the first floor because of all the heavy machinery that's installed there. You don't want to shake the building. And it's part makerspace and part, like say, contract engineering service bureau. And so I worked there for several years picking up overflow work when the students would come in. They bring in hundreds of interns every summer. Sometimes it would be very hardware heavy, and there was no way the staff in the hardware lab could keep up with it. And so I was taking these overflow projects. This was fantastic. I have worked on so many varied things. I didn't just like land in an industry and kept working and had super depth, got wide breadth. And I've done beamforming, microphones, speaker arrays. I built a 64 microphone sphere, which we then put a 360-degree camera on, and we took it down to the middle of Pike Place Market, and we set it down right in the middle of literally in the middle of the street, and we recorded a bunch of stuff, and then you can come back and you can put on a helmet with headphones, and when you turn, the sound moves too, right? So if there's a siren over there, you hear it over there, and if you turn like this, it's still over there. It's really neat stuff. We did all kinds of things from little piecing together Arduinos and whatever to build little sensors to I built a device there that combined a depth camera, thermal cameras, video cameras, audio, everything you could think of, and then we strapped this giant thing on your chest because it was to collect the data, right? The goal of research is to answer questions as fast as you can so you can publish your papers, right? And the work for Magic Leap, they were a great customer. They were doing some super, really advanced and great ideas on augmented reality displays. All that got upended with COVID, right? And so I also, through meeting some people at Microsoft, they weren't super excited to Microsoft themselves to bring out a product that was medical related. There's a lot of risk with a medical devices proportional to how much money you have. If you're a little company and you don't have a ton of money, then you might still screw up and you might still hurt someone and you might still have to try and make them whole. But if you're a big company with big money, then there's a lot more risk than ever the returns. So we spun off this little company, Evergreen Circuits, and with a couple of partners, I built the hardware. And so if you can't move, but you can move your eyes, you can drive your wheelchair. Super rewarding, didn't turn out as profitable as I'd hoped. All these businesses were upended at COVID. And so in 2001, my wife came out we had a lovely 7-acre lot. I miss the things I had there more than I think I miss the property. I had a 2,000 square foot workshop to myself, 22-foot ceilings, 40 by 50. The only body bothering me was my goats and the sheep who would occasionally butt heads and shake the whole place. And, you listen to the chickens from the neighbor. And it was a great place to set up for contract work. I just lay out one table after another. If a customer came by, I can just throw a sheet right over the top of the other people's work, and I really loved living there. But my wife came out and she said, and this is, I'm bringing this up because this is relevant to how we've gone from Altium to KiCad. Okay, my wife came out and said to me, "Why are we here?" And within 15 minutes, the question was, "Where are we going?" Okay? And 100 days later, the house had been utterly polished, the floors sanded, repainted, and we were in North Carolina in Chapel Hill in a new house. Okay, 100 days. You know, if you're going to do something, do it. My wife is a big influence on me for that. She's great at deciding rather than hemming and hawing. I can both. I'm a professional hemmer and hawer, no doubt. So, you know, before I move on to this slide, I'm going to tell you some advice that I tell all my customers. I tell all of them. Trust your experts. You hire them for a reason. When your expert's saying, well, maybe you could ignore them. But when they're banging their shoe on the table like Khrushchev, and I'm dating myself a little bit, right? When they're banging their shoe on the table, listen. So when we landed in North Carolina, I had promised my wife I wouldn't start another business myself. So I found at that point, I guess I was employee 6 at the startup. And I was glad it was just really refreshing to find a place with founders and funding and exclusive, hard to construct, hard to compete with technologies. And so it was really just a great spot for me to land. NCX makes innovative X-ray tubes. There has been almost no change in the design of an X-ray tube since 1895. You heat a piece of tungsten on one end of an evacuated chamber. It's got to be ultra-high vacuum. There can't be any particles in there. And you heat it up so hot that the electrons flowing in there that you're heating it with, they actually they leave the edge of the metal. They're not far, but they leave the edge of the metal. So if you put a high voltage across the way on an anode, you could rip those right off. When the electrons hit on the other side, they are going to return to ground because you got to make all your electrons go to ground. And they got to slow down. And when they slow down, they let go what's called Bremsstrahlung radiation. And it is a broad-based radiation. It's X-rays. You have to hit tungsten or rhenium. But you don't need a lot of that. So you attach that to a giant piece of copper and so that it doesn't overheat. And so the big difference is that if you have a traditional tube, you have to heat it up and cool it down. It takes a moment to heat up, takes a moment to cool down. You can't put two filaments next to one another because if you heat one, the other one will start to drip out electrons also. So it's hard to do basically tomography, right? Computer-aided tomography with a traditional X-ray tube. So what they do is they take one tube and they spin this thing on this multi-100-pound gantry. And if you ever watch a YouTube video of one of these with the cover off, you may never want to get in one again. It is amazing how much stuff is in there and how fast it's moving. And, just like you have two eyes, and you can sense depth, right? You can, and I did this at Microsoft, you can make a depth sensor where you have two cameras, or one camera and two lights. You flash the one light in the infrared, you flash the other in the infrared, assuming that you're not standing outside where there's a lot of infrared, and you can piece together those two images and you can get depth. So with our devices, we can stick them extremely close together. They're a current-based device. They turn them on immediately. They're made out of carbon nanotubes that are little pipes that are 3 to 5 atoms thick. This is our special sauce. This is what NCX is on the map for, is how to make those nanotubes, how to attach them to the substrate. Everything else is pretty much the same. The biggest difference is now you've got something that resembles an LED. So it's the analogy from an incandescent bulb to an LED is really similar. And so these guys were super fortunate when I got there, and they said, we want to do massive arrays of current-based things that are pulsed. And I'm like, I made a 3D TV with 256 of these things. So that there on the right is my creation there. That was all those boards in there. There's 4 custom circuit boards. That box, we call it the MBCU, the multi-beam control unit, very originally named. That one does 64 of these devices. Unlike an LED, which you might do like that TV, was 256 3-amp LEDs. The heat sink on that was something else. And you only turn on like 20 at a time. and they're running maybe 3.5 to 4, maybe 3.8 volts, something like that. Our tubes are more like typically 20 milliamps. We go up to about 100. At a certain point, you're bombarding the tungsten with cathode with so many electrons per unit area that you start to make a drill. And so you'll obliterate the surface. And so there is a trade-off that affects all of the manufacturer. How small is your focus spot? The smaller the dot that you make on that target, the clearer, the higher the resolution is probably the best way of the image that you're going to make. If you have a big giant dot, you can get a lot more X-rays, but your image is going to be reduced in resolution proportionately. And there is absolutely some limits. Of course, every single customer asks us for something that, the laws of physics apply to us too, right? Not. And so I got there, and I was the first electrical engineer. I am the electrical engineering department. I am the software development department. We have another physicist who does some computational work with Python. But this is a real-time system. There's a timing board based on a PSOC, which I love, and I wish Cypress had supported more, or now Infineon, or whoever owns them this week. I wish they kept those around. They're really lovely parts. I programmed some really nice custom stuff in that to get our timing unit to be able to produce all these pulses, to pick which one of the 64 that we're going to use. And then I have another board, which is the current sink. And that is the thing we generally say we have to regulate current. We're making current pulses, not voltage pulses. And in order to get the currents we need, we're typically between 500 and 2,500 volts, right? So this is a tricky game. Like the highest voltage FETs out there right now are 3,500 volts. If you have any inductive kickback or anything like that, you got to leave yourself a little leeway. Typically, our tubes are rated to run up to the 2,000 volt limits because the cathodes do decay over time, and they change with temperature, and each one's got a little different. And so you have to regulate that current. And I wrote all the software for the 2 different processors. As well as all this software on the PC. I've got a multi-threaded Python program. I hope the GIL is thoroughly dead. For those of you who know what the global interlock in Python, I hope it dies a fast death this October with the next release of Python. It lets us visualize everything going on. We record everything, because if you have a failure at these kinds of voltages, there's damage, and you need to know what happened. You really need to know what happened. You need to, and this is going to eventually be, hitting human beings with X-rays. So you need to know that you have put out the exact amount of current that you think, that you're producing the exact amount of dose, which is proportional to the number of electrons that flow, and so you want to record everything. And in addition, we want to characterize our devices so that we can bring them through the manufacturing line. This is primarily a tool for us to use to produce the X-ray tubes. We are a manufacturing company, right? And so it's totally scalable. One of the holy grails of this technology is CAT scans with no moving parts. So if you're in an ideal world, you'd probably have 1 emitter per degree, 360 degrees, it's several hundred emitters. This absolutely will scale up on the software side on the PC. The hardware can be all interconnected to keep the timing as fast as you can. And we'd love to have a customer who would be willing to pay for us to build it. We are more focused on smaller things, like for dental x-rays is a really great advantage. There's some great studies that were done on early devices at UNC in Chapel Hill in conjunction with Duke. I guess I'm a little embarrassed. I'm not supposed to say Duke in a name if you live in Chapel Hill. And quite the rivalry, but they did some great work with dental x-rays where you can see a 3D image of your tooth. I mean, we've all gone to the dentist, and the dentist is like pointing at this blurry image because your tooth is irregularly shaped and the whole thing's been flattened out, and he's going, clearly you've got a cavity. And you're looking at it, how? right? With this, you see the holes. In the study, they found 38% more cavities, right? This is money for the dentists. And also, I've experienced this, unfortunately myself. You get a cavity in between your teeth, and sometimes it's not obvious which tooth the hole is in. And then they go and they drill a hole in the tooth, and it's not the right tooth. And then they have to fill that, first they have to tell you that, right? Get over the embarrassment, tell you that. Then they fill that tooth, they drill the other tooth, they bill for one tooth, right? This is going on all day long, all across the world. Dentists accidentally, for these kinds of tricky things. But you can take that tooth in the image and you could rotate it around and you could really see what's going on. So our technologies are relevant to anything that does x-rays now, from searching for, scanning a backpack left on the side of a road by the parade, right? To dental x-rays, to scanning your suitcases going through luggage. Everywhere x-rays are relevant. All that technology and all the advancement that's occurred there in computing and visualization, all that's utterly the same. And so, but what's not the same is the ability to stick 7 emitters in a device, yay big, with a 14 millimeter pitch, and produce these images in very rapidly with no wasted dosage on the way up and down, so that you reduce the dosage that's being experienced by the patient. Doesn't matter to your luggage, but it matters to people. And this is what NCX does. I've been there, it'll be, I guess, about 3.5 years. I've done 20 boards, 14 with Altium. Some of these were just revisions of the same thing. Some of these were super simple little interface boards with Zener diodes to protect us from shocks that are right up on top of the tubes versus this box, which is way down along lots of cabling, right? And others of them are super complex. Like the current sink has a 480 megahertz processor on there with a ton of RAM. It sits, Ben Franklin got the sign on the electrons wrong. And in electrical engineering, almost nobody cares. But when you're actually trying to shoot electrons at stuff, you care. And so we're at negative voltages. And so I have to float the whole circuit we generally float it at minus 2,000 volts and use a simple low side current sink to regulate that and produce the pulses. This has got megahertz. We use the ST-H743, which has 3 2.5 megahertz 16-bit ADCs on there. It is the cheapest way to get high-speed, high-resolution ADCs out there for sure. But you got a lot of code to come with that, right? One of the other speakers was talking about how to simplify down your boards to teach new students. My God, the H7 is a 3,500-page document. 3,500 pages. It goes on and on and on and on. So I picked Altium, right? I was the first EE. No one else there knows this stuff. And I said to myself, all right, well, I don't want to play around. We have some funding. I'm going to pay to get a tool that I know and I trust, that I've used a lot. It was a pretty good value proposition back in the day, right? One tier, one price, all in. When I started stuff, you would get your schematic capture for $6,000, your layout for $12,000, right? You pay 25% per year for support after the first year, right, per seat. And so your engineers doing the schematics, you didn't want to buy them a license for the layout tool, because then you're paying for that tool to sit and rot for the most part. So you use external service bureaus to do your layout. And I always would go and sit with my bureau and do all the placement with them, right? But you can't do the placement at the same time as you're doing the schematic. which is kind of important because it can be iterative. You start doing the placement, and then you realize, oh, geez, that resistor is way bigger than the part it's next to. Or, oh, geez, I got to stick this right over here or right over there, and there's just not as much space as I thought, right? And something Altium does a fairly good job with is dealing with multi-channels. When you have a highly repetitive circuit board, and I thought, oh my gosh, what if I have to do 16 or 24 of these on a board? We eventually chose 8 so that we could have little modules and we can scale in groups of 8. But what if I have to do 24? Oh my God, I'm going to have to lay out the same thing 24 times. I don't want to do it. And while I had seen that I used KiCad for Evergreen because we were a little company with no money. And it worked. It was a simple board, and there was no problem. But there was some scripts to do multi-channel designs, but it wasn't perfect. Altium does a good job with that. I can't say they do a great job with it because you can't number your room, your channel from 0. It must start with 1. What? It must start with 1. And that is a flaw. I don't understand exactly how that happened with them. I'd have to get into the code, which is a problem, right? And they also have their library's really extensive, and it's very easy to just search, find a part, grab it and pull it into your design. You can't always find everything, but you find most everything fairly easily. There are a lot of inconsistencies. That thing's been around a long time. It's not really been scrubbed great. Also, Altium does something that I don't like, where it's like 1 resistor per part. And I'm like, no. There's a resistor, and then you put whatever value you need on it later. And so you might discover that you go and you grab the red LED, and then you grab the green LED, both from the same vendor. They vary with 1 letter in their part number. And they should be exactly the same, but the footprints are different because one was made by one guy and the other was made by somebody else years later, right? And so, it's all right. The electrons don't care how pretty your board are, right? I also thought to myself, and this is an important piece, right? And this is partly why I'm here, is because KiCad has to become popular for me to recruit people who already know KiCad. If I find someone with 20 years experience who's used 3 CAD tools before, I'll train them to use KiCad in a week, right? But what happens when you don't have money for a principal engineer? You only have money for someone more junior. Or what if the work you have is you just don't have work that will keep a principal engineer interested? And someone who's more junior is going to be excited for this high-tech stuff. You have to have a talent pool. And I thought, all right, well, these are the tick boxes. These are the important things. Altium does it. Let's just jump in. Now, I have to tell you, everything I'm about to say I've said to Altium directly. I am angry at them. I have said it directly. When I canceled our subscription, I sent an email to the CEO of Renaissance. Now, this is my humble opinion. I think they got ripped off. And I think they are going to write down nearly the entirety of their investment in Altium after they devastate their customer base. Okay? My opinion. I hold no stock in them for good reason. I like Renaissance's parts, by the way. They have some very nice parts. And unlike the H7, their equivalent processor has 1 kind of timer, not 8 kinds of timers, right? They're all 32-bit. They're all exactly the same. They're easy to work with. There's a lot to say for this company, but boy, not for Altium. If they had bought Altium and showed the CEO and the head of support and the head of software development the door, I might still be a customer, and I wouldn't be talking to you now. Support back in the day was great. You guaranteed an answer rapidly. Then it was, only during the week. Okay. And then it was like, well, we'll get back to you in a day or so. I sent in a support request for a problem I was having and got 0 response for 6 weeks. 6 weeks. What was I paying for? They push you very hard to Ask your questions first in the forum. Well, I don't want to leak my designs to the forum, right? I don't want to ask all my questions in public. Some of them I don't mind, but others are going to really have to reveal what's going on. Maybe I'm running into a bug. I got a problem in an output generator. I'm not going to go put my Gerbers up there and say, hey, can you open this up and tell me why it's broke? There's virtually no way to request a new feature there in private. The support staff is not equipped for that. They go out to our publicly thing, put your issue request on there, and do it in public, and make sure you give everyone that you also like a thumbs up so that we can ignore those whatsoever and do whatever the hell we want because we really don't care about you. They are fixated on getting your intellectual property locked up with them. Now, I'm not the one saying this. They are. If you read the documentation that they published to their investors on their acquisition, they said flat out, our customers are sticky. What I heard was, I'm stuck. I'm from New York City. I'm not sticking with nothing I don't want to. The software is riddled with bugs. It crashes 1 to 3 times a week. It is astonishing to me that a piece of software that old could crash that often. There is numerous inconsistencies in the UI. If you go to draw a room, which is a polygon, and then you go to draw a zone, which is a polygon, and you go to draw, there's 4 ways you can draw a polygon. 4 different ways you're drawing a polygon. The rooms one doesn't work worth a squat. If you start out with a square and then you decide you really want it to be shaped like a B or a P, oh no, you can't add any more points to it. I've reported this to them numerous times. I've told them if you don't fix these things, I'm not renewing. They ignore them. It is not my job as the electrical engineer paying several $100s a month to also be the software development engineer for Altium. It's not my job to also be the guy who is providing my own support. This is not right. That's the whole point of someone like me who's a user who is looking for this value add. I'm paying good money for a reason. There's a bug in the file output generation has been there for years. The whole point of this software is to generate the files. I got bit by said bug. I reported it. It was okay. I could work around it. Years. It's now in 2025, it's a terrible value proposition. There's 3 tiers, there's 3 prices, and they haven't added a single feature in the bottom end tier in well over a decade. There is nothing new and useful that will help you make a circuit board that has been added in at least a decade. You get less value for more money. Everything out of them is, hey, it's in our other tier. Enough. They will not get one more shiny penny from us. Not one more. So then the question is, why KiCad? Right? Because I have money. I could have gone to Mentor or Cadence or whoever. I could have bought something else. And, I used it in the past at Evergreen, and I was really impressed with it. It had some things that was missing, but in version 6, this was a viable tool. I was quite successful with that. I can say now, especially with the things added in version 9, there is not a single circuit board that I've worked on in my entire career that KiCad can't make. I've done a 138-page board, cell phone, this big, okay? We used every PCB manufacturing process that you could possibly think of. Tiny vias, any layer interstitial vias, so we had no through-hole vias. Everything's micro vias the whole way. That built the whole stack up one at a time. 1,500 components from 104 different vendors, right? I'm telling you, you can make that board in KiCad. I don't want to go all the way back to the beginning of my career, but let's just go back to, say, 2005, right? In 2005, I was not sitting around saying to myself, oh, if only the schematic capture could do this, or if only the layout can do that. The tools were fine. We were paying 20 grand a year. It was fine. They got the job done. KiCad is far better than everything that was sold back then. Now, everything that was sold back then is improved except Altium, right? But at this point, you got to customize rules. They work great. We do high voltages. We got all kinds of complicated rules. I got high voltages on the same board as tight pin pitches on a ball grid array because we couldn't get the part in a bigger package, right? Things went sideways for a while. If you've been in this industry more than 3 years, and you know the pain that happened after COVID. And it can do multi-channel designs. It's got output jobs now, so I can get my files pretty rapidly and consistently. When something doesn't work, I can go look at the code and discover, well, can I work around it? Maybe if I do something different, it'll be fine. Like this bug that I reported to Altium, the output generation, if you literally chose not a true type font, the problem went away, right? But how was I to know that? How do I know maybe it's just so broke, you're stopped? Okay, fine, I'll deal, right? But at least it gives me a chance to look at the code if I want to. Maybe I discover, oh, geez, I'm trying to use it in a way that's not the way the developers ever thought anyone would ever use it. And if I just use a different steps, I'll get the outcome I want. I love that the file formats are human readable. Because even from simple things that I do with KiCad, like I got multiple variations of the same X-ray tube, but the 125,000 volt tube has one pitch between the pins, and same number of pins, different radius for the 180,000 volt tube. And so I could just grab the file, I opened it up in Notepad++, I did a search and replace, I renamed everything, and bam, I got an exact duplicate of exactly what I changed, and then I opened it up and I modified the radius. And again, thanks to the output jobs, click, 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 which I'll get to later. There's 4 clicks. And you get what you want. And so, look, Altium's constantly pushing me to buy the vault. Now, we buy a vault from, our Mechis really love the vault from Autodesk. They use Inventor. And they love it. I have to say it's pretty good. You can just mark it up like you got a pen on a piece of paper. You could orient the thing the way you want it, and you go move this 20 millimeters to the left with an arrow, and then it's recorded so that not just that you get it fixed, but there's a record of everything that you've done. But, for the EE tools, why do you need a vault? You got Git. It's free. And, speaking of free, it's free. KiCad's free. Now, I'm going to tell you in a bit that, we're going to pay. Seth's going to land another customer. I came here in part to meet these guys and see if I was going to really get the kind of support I would want from paid support, because I need someone who can take my bugs with an NDA and recreate a new project that can be put in the public to report the bug so that it can get fixed. That's probably the most critical thing I want paid support for, because I don't want to be the QA department for my tools. I have another job. In fact, like I say, I'm the electrical engineer, the computer scientist. I have to do all the IT because I just couldn't take it anymore. And right, so I wear a lot of hats, and plus, as much as when I graduated from Carnegie Mellon, a couple months before I graduated, I went over to meet with my advisor, and I said, I just got an 18th percentile on the GRE. I don't really understand much of what you're trying to teach me about all this quantum mechanics. And it turns out much of their theories were wrong, that they were trying to teach us, and so that's why we were confused. It's because these theories don't really work. We now know all these things later. And I said, my hopes and dreams of being a particle physicist are gone. And oh my God, I'm a particle physicist now. It's super low energy. It's funny to be here at KiCad, right? You got CERN, right? They're doing stuff at the teravolts, and we were only getting up to kilovolts. But I am absolutely shooting electrons at stuff and seeing what comes out. I I could never have predicted that back then. I am amazed that I have come full circle. So we got to migrate. Migrate? What migrate? I'm not migrating. I got my existing boards, they work. One of them's got, God dang it, I crisscrossed my hardware handshaking on the UART, and there's isolators involved, and so you can't just use the software to flip the pins around. And we're going to survive because I want to upgrade that processor anyway to a dual core and with a wider memory bus and a different package because COVID is over and I can get parts in more packages. So I just ripped the Band-Aid off. I just said, that's it. I polished off all the latest revisions, corrected everything I could. The hardware handshaking resulted in a big upgrade. It wasn't just a little repair. We were really adding some bandwidth there, and so we went from 3 megabit to 18 megabit, and without hardware handshaking, you're just done. I mean, really, even at a megabit, you really need hardware handshaking on your UART. We froze all the existing Altium boards. So this is the big thing, right? At the bottom, I gotta have support. You gotta have paid support. Someone's gotta be working, supporting KiCad for money because otherwise you can't maintain your privacy. So, I wanted to change the tone. I will skip through the next sections pretty quickly because I am over time and I'm eating into lunch. Some of the things I want to talk about are going to be gone quick, right? So the first thing is library management. How do we deal with that? Well, I replicated the same idea for our internal libraries as what you get from KiCad. I don't download the libraries. Here's a feature request. I wish we didn't have to download the libraries every time you download a version. I appreciate having an official released version, but I want to pick up the libraries regularly. And so I structured them the same, and then I made a custom script. It's nothing too fancy. I started out creating my directory names like ncx internal.ncx because I thought my script would be super simple, and I would just use that little dot whatever as a prefix on all the variable names. But it turns out that's not what you want to do. You end up with a JSON file with a handful of things that you want to do. Because you want to be able to move your directories around, different users maybe have different drives or whatever. And I just followed the same thing that everybody else did. Or I say what the KiCad team did. I started with a prefix, but I'm realizing now as I'm using this a little bit that I really want a postfix because when you go in to pull up a part in the library and they all come down, if you have a prefix, your stuff all ends up at the end, which maybe is desirable. But if you do a postfix, then if you have an MCU and an MCU, because I want to copy the directory structure the same, right? I don't believe in hidden pins. I think they're super, super, super dangerous. If you have a pin on your part, you should put them on your schematic. Can you imagine sitting on a stand in front of a jury and a judge and them saying, there's been property damaged and people injured? Why did you leave that pin off your schematic? And you say, oh, it was pretty. I wanted my schematic to be pretty. I cannot imagine that. But I want to harness all these libraries. So I start with the part, and I just pull off all those ground pins and whatever, and I add them on one extra thing. So I want to have almost the same structure as everything. So I want to just update. I'm sure within a couple of weeks I will have updated that script to postfix. I will update my few boards so that they now are well, I may not even have to because of the environment variables. If I change the environment variables, everything should move. Maybe some of the symbols need a little tweak. I have not automated adding this into. I get 3 output files, right? The footprint symbol library, the symbol footprint table, the symbol table, and another file which just got these environment variables. I copy those into the configuration file wherever that may land on Windows. It's buried, right? At some point, if I had some staff to write some software for me, it would just put those right in there. but I don't want to get into opening that file, not ruining it. And what if there's already got the stuff in there? How do you deal with overwriting? You do this once when you install. It's not that big a deal to just copy and paste it in, right? When I build up the library tables, I scan the directories. Maybe I should look to see if there already is a symbol table in that directory and then keep that. But all the descriptions disappear. I don't find that a hardship. I know what I'm looking for. I'm not looking to my symbol table libraries to tell me what's exactly in them with a one sentence. So it's not a hardship, but I do lose them in the way I've done this. So I want to point that out. So there's going to be no time. The script is not rocket science. It's Python. It's really not that hard. You open a configuration file, you read out the things, you build up some dictionaries with the names of everything, and then you call a function that spits out the 3 files. Right? So with that, and I will really definitely try and pick the pace up here because I got quite a bit of slides, but I'm fond of saying that engineers don't make products, they make the files that other people use. They make the plans that your manufacturing staff uses to make what you want, right? So output files to me is critical. It is the whole reason I'm there. I want to generate them automatically. There's tons of files to generate. Depends on your manufacturer. You may need one thing or another, but maybe you make them all because depending on the board, you send them to this guy. Sometimes you send them to that guy, right? And you want it all to happen right away. So over the next couple of slides, I'm going to point out I'll go through it pretty quickly, but I'm going to point out there's some quirks in the way this is all working right now, right? So all my comments were for 9.0. Oh my God, 9.0.2 is already out. I just, I got on the airplane, it wasn't there. Here I am, it's there. This is great. There's some big bugs that were in the job sets in 9.0.0. Move on to at least .1 right away, because otherwise you may open your job set file and see nothing listed there. And that bug's fixed. I got 16 steps. And theoretically, you could have one click, except there's some quirks, and so it doesn't quite work. So I'm going to rip through these steps real fast. Okay? I click on Do First, and the first step is I make my output directories, a little bit of Python. I like the idea of putting the Python right there. I don't want to call in this output job a separate Python file that now with the output job I got to pass little scripts. So this is great that I could just squeeze the whole thing in there. I do edit it in Notepad++ first, and I keep around a little file for me, but then I paste them right in there. All I'm doing is I look for stuff. If the directory's already there, I remove any files that are there, so I'm starting off clean. And then I'm assuming that when you get to the end, because I'm wiping this out each time, that you're archiving it. Either you're doing a check into Git or you're zipping it up and putting it elsewhere. That you're not going to accidentally wipe your own tools. The version of the files that you've already sent off to manufacturer. Okay. First, I generate an ERC. It's okay that you have errors. Every board I've ever made has ERCs and DRCs. You look at them and you go, that one's irrelevancy. Oh, your silk screen goes off the edge of the board. Yeah, but so does the connector. So who cares, right? There's certain errors, but don't do it blindly. Record it when you're making your output files, right? Now this is where there's a weird quirk. Okay, I want to generate a PDF of the schematics. If that says output directory, you cannot control the file name from this dialog box. You can only pick the directory. So for this one, for the schematics, I don't put in a directory because I'm going to rename it later with an execute command with a bit of Python, right? But for some reason, it doesn't show up until you actually exit your process. It's often a temporary directory. I found it, but it's temporary and it's named arbitrarily. And so you have to actually exit your little process there. So I stick that in the... Everything's getting put under outputs, which you do in your project, right? I move on to the PCB. I do a DRC, same thing as before. It's okay to have them. Just write them down, keep track of them, right? So now I generate what I call my fabrication drawing. It's got the notes that Sierra or whoever likes to see. And again, it's going to be project name.pdf. That's what you're getting. So I stick this one in the PDF directory so I don't overwrite the schematic one from before, right? And then I get to my do second. Where there you can see I set the destination path to outputs, right? So one line of Python, and I can grab the file name, and I could rename it. Instead of project name, I could say PCB top view, because I do a top view and a bottom view. I get dimensions all on there, so, to go along with the step file, right? So now my first step in the do second renames that one, and then I export the bottom. But I got to stop again because it's going to have the wrong name. So I come down and I rename it. And now I'm in my last step, which does a lot of stuff. It's super fast. I'm really impressed with the pace at which you get output file generation here from KiCad. It's super fast. So I rename the other one to bottom view, and then I generate my BOM. Oh my God, this is such an art form. Some people demand it all happen in the schematic. I tend to think you're better off to do it in some other tool that's better capable of dealing with substitutions and all that other stuff. And in the same breath, I can tell you for sure, I know of a product, they make over 100,000 units roughly a month. And that whole thing is being done with Gerbers and an Excel spreadsheet, man. That's it. I mean, it's a $15 million robot that puts the product together, right? But the circuit boards, that's it. That's all it takes. You can do more. If you can, do it. I export a step file. This goes a long way to making your mechanical engineers happy. Otherwise, they're going to be looking at your little fabrication drawing and trying to make up something equivalent. In the same breath, put your dimensions on your fabrication drawing. It's important, because they're going to be looking, in their 3D viewer, and they might want to just go, oh, geez, what is the pitch between those connectors? Oh, I put them on a 20 millimeter, right? And it's readily obvious. I love the component output filtering. A lot of boards only really need J star, right? Just your connectors exported, things that leave the board. That's it. Mounting holes, and that's it. And if you start pulling together, as I did, to make that MBCU, that sheet metal was done in FreeCAD because I don't know anything better, and I needed it done. And so, you start rotating around 5 circuit boards stuffed with components, and then I make an array of the other ones, and oh man, you really bog down your machine. So being able to just export what you need this is a great feature, missing from Altium. Now, I don't want to sound like I'm a guy who only throws around. I changed this last night. I don't want to sound negative, right? I don't want to sound like I'm like the kind of guy who just walks around crapping on everybody, right? So I want to shout out a couple of my vendors here. I use out-of-the-box manufacturing. They're in Renton, Washington, just south of the airport. They're a nice factory. It's clean. They got plenty of lines. They can follow all your ISO standards if you need. And I have done a number of projects with them, and they will do turnkey straight into a box if you just tell them what you want. I have not used that feature from them, but they are great. They are manufacturing a board for me as we speak. They ask for GenCAD if you're going to give them Gerbers. And so there is no GenCAD selection in the job sets right now. Glad to hear it. Because while this is great, I'm a programmer, right? So I look at that and I'm not phased. But not everybody has been doing this for 40 years. And they look at that, they just want a GUI. They just want to click on the boxes. So, hey, the star of the show, you generate your Gerbers, right? And this is great. I got nothing else to say about it. You pick the choices, you hit the button, you get your Gerbers, right? Here's where I got a little bit of a complaint. You go to generate your drill files, and they don't end up in the Gerber job file. And so another vendor that I've used a lot, Pentalogics, they started out making software for people doing fabrication, right? And so they ended up being like a contract broker for circuit boards because they had the software that can pull in these circuit boards, panelize them, and they piece together everyone's little jobs, and they have pretty great rates without going to Asia. And I've used them a lot over many years. In the same breath, they can go to Asia if you want. And I always believe that you should validate your outputs with some tool that's not the tool you made it with. So I've never opened up the Gerber viewer from KiCad. I've never used it. I've been using ViewMate forever. I trust it. I've made a lot of boards. When I look in there and it looks right, I get the board that is exactly what I like. The viewer is free. I encourage the development team to download it and try it because you'll see on the next slide there's some issues. ViewMate doesn't deal well when you grab the zip file with everything and it finds a Gerber job file. It assumes that if it's not in the job file, it doesn't exist. It doesn't continue to parse, so these extra files aren't found. And that's a minor annoyance. For circuit boards, too, I use Saturn Electronics in Michigan. They've done metal core circuit boards for that 3D TV. They do Flex also. I've used them here at NCX because we had some stuff that had tiny vias, and I just didn't want to throw it to a broker. He would have done it, this fellow Greg. It's nice to actually get human beings at Pentalogics, but I had to send it overseas. And this project I couldn't send overseas. And then if you're ever doing Flex and you need 1 mil vias on a 3 mil pad, I hate to tell you I needed that. Oh my God, your choice is microconnects or nobody. I am floored with the accuracy. And Flex, they move. When you start hitting with the laser, the Flex starts moving. How they get such tiny vias on such small pads, I don't know. They told me they could do it. I believed them, and it worked. Now, I'd love to move to IPC 2581 because I'm as done with Gerbers as everybody else. And I will wrap this up in a minute here, okay? But they don't open in ViewMate right. There's something not right, and they don't open up in the WISE 2581 viewer right. So again, my message, I'd like the team to grab a couple of these other viewers and try and view these netlists because they're not working right. And, these will get resolved. These will get resolved. And I'm not hearing people saying, hey, I used the 2581 netlist from KiCad, it didn't work. I'm just saying I got nervous, and so I went back to Gerbers. I knew what they were going to do. Same thing, the ODB++, I know that's brand new, but it doesn't open up in ViewMate. And so, because I thought, well, if I can't do the 2581, I'll do ODB++. And that's the last step in the do last, right? So I got my 3 clicks, everything gets named, right? And then not everything shows up until it ends, so you got to end. And I have this little bit of script that zips everything up so that I get one set of files from my fabricator and an additional set of files, includes the fabrication stuff, but other stuff too that go off to the assembler. So I got the 4 buttons, and it's click, 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 done. This is fantastically important to me. And so this is my last slide, right? We do things with extremely high voltages. When things go wrong, we shoot literal lightning bolts. I destroyed $8,000 worth of equipment until we realized we weren't grounding a piece of nearby equipment. It was left floating, and then it would charge up capacitively under this massive multi-100,000 volt field that's nearby, and then whack. And oh my gosh, I'm sitting there and I see it. I got a scope probe sitting on the desk, and it picks up a 500 volt peak-to-peak signal, right? So safety first. You know, I'm the EE. I'm the guy who's going to turn this thing on the first time. Safety first, right? We were luckily, everything was an enclosed lead room with an interlock, right? So we were just watching the aux shoot on video. But I would not use KiCad if I thought my life was in danger, because these things will kill you. 200,000 volts, there's no may, your heart may stop. Your heart will stop. I got a power supply, came 80,000 volt power supply. I kid you not. The cover page shows a picture of the supply. You open it up, 20 pages, how you do mouth-to-mouth resuscitation. Call for your ambulance first, right? Make sure you're not going to get shocked in addition, right? If it's good enough for us, it's good enough for you, right? So this is the end of my talk. You can contact me if it's work-related. You can contact me at NCX. If it's just more generic KiCad, this is my personal email that I use. I'll warn you, if you talk to me, I will be your friend. I cannot make enough friends in this world. I am an utterly social person. I will be taking the train to Old Town for some Mexican before I go to the airport later if anyone wants to join me. And so this is the end of my talk.